different argument than our expectation did.
So difference given आपने दो से भी f of u लिखा है फिल्टर से
Yeah.
f u है f s है
fs किधर ये
नहीं लेफ्ट
ये t है ना सर नहीं fs
s तो definitely w
yes it should be yes it should be everything yes ठीक है so the martingale-ness of the stochastic integral the process defined through the stochastic integralness is really preserved actually. Now let's think about talk about some more properties of this. I'll prove that and give this to you that okay, you read it for yourself. The next thing that you can do is you can show that this martingale-ness, in other words, the stochastic process that you have defined through the stochastic integral is not only a martingale, but it's a continuous map. So it's a continuous process as well. Okay? So we need a continuity property. So what does this say? It says that suppose you take f an arbitrary from L to AD. Okay. In other words, okay. So what would be the so this is like another advantage of it. I mean, for example, in Riemann integrals you don't have this continuity property that if a sequence of numbers converges to a sequence of sequence of functions converges to, for example, in some sense to a function, okay, then the Riemann integrals does not necessarily, it doesn't respect, okay. So we saw this that if you replace this Riemann integration definition by, for example, what do you say? Lebesgue, then that is preserved actually.
It is an operator.
But it's also preserved in this case actually. This is just a particular manifestation of what we have. Okay? So suppose f is from L to AD and mt is the integral from A to T f of u and wt. F of s dws. Okay? Then mt, okay, where T is in A to B as is continuous actually. It's continuous. That is that almost all paths if you take any path of this process and you look at it for the entire time A to B, this would still be continuous actually. Is continuous at on A to B. Okay, so it's a continuous function if you see it from the perspective of T. Shall I go into the proof? So how many minutes do we have? We have yes, we can go into the proof. Okay. So here's the thing. So you start with the case that okay, let's assume that when f is a step process actually. Okay, now let's prove this continuity property for a step process. So f is a step process. That is f of t can be written as I equal to 1 to n, so I minus 1, obviously, times indicator function of, say, t I minus 1, yeah, something like that. Okay. Be careful about the orientation of the interval, something like this. Okay? And where xi minus 1 is fti minus 1 5 below. Then I know for mt, what would be the mt in this case? Is going to be, okay, I equal to say 1 to k. It's not going to be, you know, entire interval, because okay, this is a description for t in the intervals, say ti minus 1 ti. Okay, now that's so this guy is defined, should I say, t in a to b rather than t in a to b. So this is a description of it for a to b, but you have to define the integral from, or you have the integral from a to t actually. T could be an arbitrary instant, so shouldn't go to the, you know, should, so it's like a sub-partition of the interval a to t actually. Okay. And then this must be same as, so how can I define it? What would be mt using this process? So I can write this as xi I minus 1, obviously of omega, times the indicator function, not indicator function, times the increment of the Brownian motion. Okay, so w of ti minus w of ti minus 1, okay, plus the increment as this arbitrary point xi k minus 1 times b of t omega minus b of t k minus 1 omega, because this t could be an arbitrary instant. It's not necessarily that this t is exactly one of the points in, you know, in the partition actually. So it could be in between as well. Okay. So in other words, you know, t could lie between tk minus 1 to tk. Okay. So for this part, I know I have, you know, integral, but then you also have to incorporate this part as well in the definition. Okay. Now, is it continuous? So this guy is measurable, random variable, so you know, it's not changing over the time. But for the Brownian motion, we know that it has continuous paths by definition. Okay, so this entire guy, you know, is continuous. If you want to see it, you know, from the omega perspective, you put an omega, so it's really continuous actually by definition.
So W
yeah, W होना चाहिए. Okay. So for F, you have the contradiction. Can you guess where I'm heading? So now I'm going to say that let's take an arbitrary F from L. Okay, arbitrary F from L. And then I can find a sequence of step processes that approximates F in LTV sense actually. Okay. And then I know for the sequence of roughly what I'm saying is that these step processes, then the integral is continuous actually from A to T. Okay? Then I'm going to show that if you're going to pass the limit, the the continuity is preserved actually on the stochastic integrals of f and z. That's what we would like to show. Okay. And we also say that is that limit n goes to infinity, integral from a to b, expectation of fn of u minus f of u square, not a to b but a to t, okay, and it's 0. Okay. So I can, from this sequence I can choose a, so in other words, for every epsilon positive I can find capital N actually. Okay. I can play this epsilon delta game actually. So in other words, I can choose a subsequence such that if you have, say A to B, so this must not be A to B, but it should be A to B, it should be A to B actually. Because this is approximation over the entire interval. So I can choose what? I can choose a subsequence which satisfies this actually. The expectation of fn of u minus f of u square can be estimated by, say for example, 1 over n raised to 6 actually. Okay? 1 n raised to 6 for n greater than or equal to 1. Okay, the subsequence is being denoted by the same, I mean, you can write fnk's if you wish, but just denoting it by the same process. Okay, so it's just really basic forms. Okay, now the next. You see, I intend to apply Borel-Candeli. So try to make a picture in your head. Actually, what should be the subsequent steps actually. So define a process xtn is the same as previous one, that if you have a to t, okay, fn of f and d w of s, where t is an instant between a to b, okay. Then we know that for xt, since this is the stochastic integral of a step process, it has continuous path actually. Xt has continuous path. As if it must have continuous paths. So you just showed it. If you take a step process and you can see that its integral should have continuous paths. So this must be has continuous path. Okay. So it has that our required property. And I also know that this MT and XT are martingales. Okay, so we just showed previously that MT and XT both are martingales. And I want to use the loop, the submartingale inequality. So the loop submartingale inequality is going to look like this: that the probability that the supremum of MT minus XT n, where the t is being chosen from A to B, can be estimated by say n. So epsilon is like n. Bigger than or equal to 1 over n can be estimated, 1 over n can be estimated by 1 over epsilon, which is n, times the expectation of what?
MT minus XT.
MT minus XT, or I can take this final value actually. So it could be also MB minus XB n actually. So this would still be true actually. So I can have this estimate. Okay. Now on this guy in particular, I can apply Jensen's inequality. So what Jensen's inequality I'm applying? So I know that expectation of x squared is less than or equal to square root of expectation of x squared, right? But I can get rid of the square and put a square root here actually. So I'd like to estimate this by what? I'd like to estimate this by n times of
Square root of expectation of.
if you wish, you can also put an square root of expectation of
NB minus x.
okay, so mb minus xb n squared. Okay, and I can estimate this by. I can estimate this by, can I say that n times of, so what would be the description of this actually, mb minus xb is square. So mb is the integral from a to b, and xb is
The integral of a to b fn minus fu.
So it's going to be square root of a to b, okay? And expectation of, f of u minus fn of u square and du, right? So it's going to be something like that. Take it?
Expectation value over.
True. But I can apply e to isometry. So the expectation of the stochastic integral is going to be equal to the expectation of this actually. And for this I have an estimate. For this I have an estimate. So this estimate can be what? So I can estimate this side by n times of square root of 1 over n power 6, so it's going to be 1 over n cube, 1 over n squared. Okay. So I can say, this goes to 0 and as n goes to infinity. So this goes to 0 as n goes to infinity. Take it? Alright. Then I can say that if I define ans by those omegas for which this supremum of mp minus xt, mt minus xt, n goes beyond 1 over n. Then I know this is showing that probability of an goes to 0 as n goes to infinity. Okay. In other words, as n goes to infinity, these events become unlikely actually. So these events are become unlikely, okay? And then you can write it in the, using the Borel-Cantelli, you can write in that the probability of, n goes to infinity, the probability of the lim sup of ans, are an occurring infinitely often. Okay, so there are different notations. You can write this as, an occurs infinitely often is same as lim sup of, ans is same as the union of the intersections. Actually, so this is just all these are notations. So this becomes improbable. So in other words, an would occur infinitely often, is an unlikely event actually. Is an unlikely event. So if you take, for example, the complement of it, so what would be the complement of it? Complement of this, in other words, you're going to say, and goes to infinity, the probability of these being less than or equal to n has, 1 over n has you know, they'll occur almost surely. They'll occur almost surely. And complement is 0. So I'm not writing a description of k and complement. Okay. So we are almost there. So what does this entire analysis shows? That the trajectories, okay, of stochastic integral of f and the trajectories of the stochastic integral of step processes are not going to differ infinitely often actually, as n gets bigger and bigger actually. So they tend to be similar actually. Okay. Thus, I can say, in conclusion, for each omega in omega, this guy xn, at any instant omega converges uniformly to x per m of omega actually for each path. I mean, in other words, you fix a path, then what does this show? That this converges uniformly.
So not a subscript.
Okay, so the subscript means arbitrarily. Okay, so I can fix a t actually as t. But this would not be really about t, but no matter what t you take, this would be true actually. So sometimes if you want to show the arbitrariness, you put a dot actually. You put a dot. Okay. You put a dot. Now, we know about the uniform continuity, that it really respects what do you call continuity. Okay, it really respects the continuity. So in other words, you can see as each of this xn, okay, of t is continuous, so uniformly continuity, kind of roughly makes sure. So I mean, you can read the precise argument from book, but this shows that the continuity would be inherited by this as well. Okay, the limit as well as n goes to infinity. And that's it. I mean, just see the the rest of the argument from the book. Actually, okay. So not getting into it. It gives a very precise argument. Just read it through here. Okay. So what we show that if you have a process and you can find a sequence of a step process that can approximate in L2AD sense, and the sequence of the stochastic integrals of a step process would converge, okay, how do you call the stochastic integral of the process M actually. Okay. Yeah, that's it. Shall I? Okay. I'm not. If you can give me when you have an accident, कब है next? अभी है? चलो ठीक है. So just like to write a formula that really is the crux of it, that which makes so in other words, engineers like that final formula actually. Okay. And the final formula that I'm writing is that you can, and it has been shown, you can read it from the book, that that if you take f from L to a D, okay, then A to B, f of t, dg of t can be seen as the limit n goes to infinity of I equal to 1 to n, evaluate your f at left end point times the increment of WTI times increments of WTI minus WTI maximum. Okay, in L2 omega sense. Okay, so it's in the book, you can read it. So why this is a heavenly formula? Why this would be a kind of a, formula that the engineers are really going to like it? Because what does this simply saying that, okay, not ddt, but obviously dw. Okay. Alright? Why this would be a heavenly formula for engineers? Think about it. So you want to compute the stochastic integral of any given process which is here, partition the interval, compute the f at each left end point, and multiply it with the increment of the Brownian motion, and just have a look at where this sequence of the partial sum converges actually in L2 omega sense. In other words, just take the expectation of, square it and take the expectation of this actually, and see that where does this goes actually as that goes to infinity. Okay. So from simulation point of view, this would be really the key thing actually. I mean, you want to simulate, for example, the trajectories of, say, the stochastic integral. Your algorithm should do what actually? Okay, you should know how to simulate these Brownian motion. Just evaluate, for example, f at each left hand point of the interval, and then see where it goes actually. So from a simulation point of view, it becomes very simple. Okay. So in long run, if you want to keep something in your memory, that's the key formula that you should keep in your memory actually. The rest of thing is just to justify this guy. Just to justify this guy, that why this must be something that is interesting actually. Okay. So it's in 1.7 section that you can read it for yourself actually. But that's a beautiful formula. It summarizes everything. Okay. The crux of it. ठीक है जी.